we are given this situation here where we have a beam that's shown here of mass 10 kilograms and length 1 meter from one end to another. It is suspended by a string. The string makes an angle of 35 degrees with the beam, and then it is holding a mass of 3 kilograms that is 25 centimeters from the end. The first question is to find the torque due to each of the forces present in the situation shown. Now, what we are shown here is in equilibrium, meaning that we don't have any motion in any direction. In particular, we don't have any rotation. So, strictly speaking, we can choose any point here along the beam as the axis of rotation. But it is more convenient to choose the point at the pivot. It is more convenient because then we can handle with it the forces exerted by the pivot. Now, what are the forces acting on the beam? We have the pivot acting on it with a force. For simplification, that force, we break it into two forces. One force, we say it's a horizontal force. Force along the horizontal, like this. And then the other force on the pivot here, we call it a vertical force. F vertical. Now we have these two forces exerted on the beam due to the pivot. Then there is the force exerted on the beam due to the gravitational force, its own weight, Fg. So this is exerted by the Earth. And then we have the forces, the force exerted by the pull from this mass, and that's going to be equal to the gravitational force acting on this mass. Let's call it Fg2. And then there is the force exerted by the string, so Ft. So we have in total 5 forces acting on the beam. The question is asking us to find the torque due to each of these forces. For 2 of these forces, the torque is easy if we choose the pivot point as the point about which to calculate all of these torques. So if we choose the pivot point here, the torque due to Fh is going to be equal to the torque due to Fv, and it's going to be equal to 0 because both of them, the vertical one is acting just below here and the horizontal one is acting just here. Both of them have a line of action that goes through the pivot, making their lever arm equal to 0, so their torque equal to 0. Now, we are left with the other forces, 3 of them. The torque due to Fg is easy, so it's Fg, which is the mass of the beam times g, times the lever arm. This is a simple geometric configuration, so the shortest distance between here and the pivot is half of the length of the beam, so that's going to be 0.5 meters. And now, if we forget about all the other forces and consider only f of g is going to rotate the beam in the clockwise direction. So my torque is negative. So this is my torque due to Fg, so it's minus mb times g times 0.5 meters, which is in this case 10 kilograms times 10 newtons per kilogram times the 0.5 meters, which comes out to be minus 50 Newton meter. Okay, that's the torque due to Fg. Now the second easy torque is the torque due to Fg2. The torque due to Fg2, so it's going to be Fg2, which is going to be 3 kilograms times 10 newtons per kilogram, so that's 30 newtons. Of course, that torque is negative because it's a gain. If it is the only torque acting on the beam, it will rotate it in the clockwise direction, so it is negative. But the distance, my lever arm here, remember the line of action is here. The shortest distance from that line of action from the pivot, it is this distance here, which is 1 meter minus this distance, which is 25 centimeters, or as given here. So it is 0.75 meters, which comes out to be minus, we have minus 22.5 Newton meter. Now, the torque due to Ft is going to be Ft, which we don't know, times the lever arm. Now, the line of action of Ft is along the string. So my lever arm is the shortest distance from the pivot to that line of action, to the string. So it has to be the perpendicular here. Okay, for this triangle here, we know the hypotenuse, which is 1 meter. And we know this angle, 35 degrees. So my lever arm is going to be 1 meter times sine of 35, the opposite to the angle. Times 1 meter. Okay, now this torque is going to be able, if it was acting by itself, to rotate the beam in the counterclockwise direction, so it is positive. We don't know Ft, so we cannot find from this expression the torque due to Ft. But we have this expression here. Now, how would we find it? We remember we have equilibrium here. If we have equilibrium, that means that the sum of all torques is equal to 0. The sum of all torques in this case is going to be 0 for the torque due to Fh. Okay, it's going to be 0, the torque due to Fh, plus 0, torque due to Fv, plus minus 50 newtons meters, the torque due to Fg, plus minus 22.5 Newton meter, the torque due to Fg2, plus the torque due to Ft is equal to 0. So solvent for the torque due to Ft, we can find it to be equal to 72.5 Newton meter. Again, I did some cleanup. So here we have the torque due to Fh0, torque due to Fv0, torque due to Fg minus 50 Newton meters, torque to Fg2 minus 22.5 Newton meters, torque due to Ft it's plus 72.5 Newton meters. But then I left the expression also we found for the torque due to Ft, which is Ft sine of 35 times 1 meter. The question, part B, is asking us to find the forces exerted by the hinge. Okay, to find the forces exerted by the hinge, one way to do it, to find the forces exerted by the hinge, we are going to apply Newton's second law of motion, which is sum of all forces is equal to ma. So in this case, the forces are the 5 forces: Fh, Fv, Fg, Fg2, and Ft. When we write that expression along the x, remember the x being the horizontal, Fh is going to be just Fh. Fv is going to be 0. Fg1 is going to be 0. Fg2 is going to be 0. And then for Ft is going to be, look at it, it's in the second quadrant, so it's going to be minus Ft cosine of 35. And that's going to be equal to 0 since we don't have any acceleration. So you notice, if I know F sub t, I can find Fh. And that's why I left this expression here. Now that I know what the torque due to Ft is, I can solve for Ft. I'll do that in a second. And then once I solve for Ft, I can find Fh. And along the y equation, Fh is going to have no component. Fv is going to be the full Fv. Fg is going to be minus Fg. Fg2 is going to be minus Fg2. Ft is going to be plus Ft sine of 35, and that's going to be equal to 0. That's my equation along the y, and that equation will help me to find Fv. Okay, I'm going to do a little more of a cleanup here. I'm going to delete the torques since we don't need them anymore. Just leave this last torque here. We solve for Ft, then we find Fh, and then we solve for Fv here. Okay, solving for Ft here, so we need to write 72.5 Newton meter is equal to Ft times sine of 35 times 1 meter. Okay, and we solve for Ft that way, so Ft is equal to 72.5 over sine of 35, and that comes out to be 126 newtons. So we know now what Ft is, so we plug it in this second equation. I'm going to erase this since we don't need it anymore. So Fh is going to be Ft cosine of 35, which is 126 times cosine of 35, which is equal 104 newtons. Now for Fv, we are going to use the y expression. So from there we have Fv is equal to Fg plus Fg2 minus Ft sine of 35, and that's going to be Fg, remember, is 100 newtons, Fg2 is 30 newtons. Ft sine of 35 is 72.5 newtons. Which gives us Fv just equal to 57.5 newtons.